So for everybody who's in the room, you can use the chat feature to ask your questions, and any unanswered questions due to time constraints will be provided in written format shortly. Also, you can make this presentation full screen by clicking on the 4 arrows icon in the right top corner. To return, click the same icon again. So with those housekeeping items out of the way, here's Patrick Roman with his presentation.
Hey, good afternoon, everyone. Our Cylindrical Ion Trap project, where what we're doing is we're making miniaturized GCMS ion trap instruments to basically miniaturize that analytical instrument. So what really has made this possible is the miniaturization of the internal components, the ion trap itself, and some other components using electronic packaging technology or semiconductor device, MEMS technology, etc. So over years of development of these components, we've been able to develop chip-based type solutions for the mass analyzers. We selected the ion trap because it miniaturizes well, and it gives us the ability to have a reasonable mass range for a reasonable voltage, operating voltage level. Okay, so to prove this technology out on the chip scale, or on the chip platform, what we've done for the work of the poster shows here, basically the design fabrication of the chips, which has been completed previously, but then integrating these chips, which are about 1 centimeter square, into an industrial available GCMS unit, but a field portable unit for on-site chemical analysis. So this is rather exciting because you know, we can take the existing instrument and plug our chip into the ion trap assembly, and basically using the ion trap assembly as an integration fixture to then operate the ion trap chip within the instrument construct. So basically what we've done here is we've gone ahead and plugged the chip into the instrument and then just run some FC43 through the GCMS, which is a PFTBA, calibrant for mass spec. It's got a lot of peaks over a large mass range, so it's a good calibrant. And what we've been able to do is, with some modification of the electronics and you know, the operating ranges of the chip, we've been able to basically cover the upper end of the mass range for the calibrant, which you can see here in the top spectrum is the full spectrum, all the way from, I think, you know, 50 Daltons all the way up to 600 something, 620 and above. And basically, that was for the ion trap that came with the system. All right, but then plugging the chip in, what we've been able to do is, you can see the shaded area here. That's the window in which the chip will pick up and scan the masses through. So it's trapping all of the masses, but because of the voltage range that the electronics within the instrument are operating over, we're only able to capture the higher masses from about 220 up to 620 and above. Okay, so that proves that the chip actually works within the instrument, and it gives us an extended range all the way up to, I think, about 1600. But the problem is we want to get the masses down at the lower range, right? So from 50 Daltons all the way up. So in order to do that, we need to change the RF's voltage scaling so it will operate over that whole mass range. So we can do that by modifying the RF electronics. Okay, and there are a couple different ways that that can be done. We can either go in and change the analog electronics for the RF power supply, or we can kind of truncate it using attenuation. But this is a rather exciting project because we've shown the feasibility of this new technology, the small metallized ceramic chip. We've shown that it works, and we've shown a path forward for modifying the electronics to tune this chip to the mass ranges that we would like it to work. Okay, so once that's done, the benefits of this technology are that the voltages that this will operate under are much lower. Probably from 50 to 500 volts versus 200 to 2,000 volts in the current system. So we've miniaturized the electronics, we've miniaturized or we've reduced the power consumption and the voltage levels that this device operates under. And what we want to do is go from this large 100-pound type device that two people have to carry around to use in the field to make it a much smaller device that can be a handheld unit. All right, so that's the real goal of the technology.
Hey, Patrick, I have a question here from John McGrath.
Yeah.
Have you tested with other reference materials or unknowns, ID, any LODs?
So at the moment, we have not. We're still really just working out the details with the calibrant. So once we get the calibrant squared away, then the plan is to move on to drug mixtures and then also explosive mixtures. So a bit of instrument tuning has to be completed first. So one other thing I'll mention is that there are two other posters in this session. One of them is the cylindrical ion trap fabrication method, which explains more detail about how these chips are made. And also micro GC gas chromatograph on a chip, which we plan to use for the front end separation method going into this ion trap for identification. Hey, good afternoon. So this poster is about the miniature ceramic ion trap mass spectrometer chip. This is a device that we developed using metallized ceramic technology. It's a back-end technology that facilitates the front-end semiconductor chip fabrication technology. So basically, we're using microfabrication materials and methods to make new mass spectrometer components, taking advantage of their materials and high-resolution fabrication capabilities to make new mass spec components so we can go down and make these instruments handheld. If you take a look at the first image here, what we've got is the Griffin portable GCMS. It takes two people to carry this 100-pound large instrument. It's a rather large machine, and it has all of the components that a laboratory instrument mass spec would have. Gas chromatograph, an ion trap, all of the vacuum pumps and inlet mechanisms, all those kinds of things. And what we've done is we've taken a small centimeter squared metallized ceramic chip that we've made, an ion trap, and we've integrated that into the existing ion trap assembly. So using that as an integration fixture, and we've tested out the performance of that chip within the instrument. So we did some initial scans using a PFTBA calibrant, and we came out with peaks for that calibrant from about 50 to 450 Daltons. All right, that's the mass scanning range of that instrument. Okay, so once we did the same experiment, but we inserted the ceramic chip, we were able to scan from 220 Daltons all the way up to about 1,200. So looking at these two mass spectra, you'd say to yourself, well, why are we getting such a mass shift? Nothing else, all things being equal in the instrument. And basically, when we change the geometry of, we miniaturize the ion trap, we make this small chip, which is about 300 times smaller than the existing chip, the existing ion trap. You can scan higher masses with lower voltages. So that's a real advantage for us because we're making a small component, a mass analyzer, and what we can do is apply less voltage but still scan the masses that we're interested in. So in order for us to recover these lower masses that we're interested in seeing from 50 to about 220, we're going to have to modify the RF voltage module within the instrument. We can do that a couple different ways. We can either change the analog electronics, or we can go in and we can attenuate the signal, truncate it to the range that we're interested in, okay? And then we should be able to operate over that 450 to 450 Dalton range, which is the traditional mass range that the instrument was designed to work over. Or if we open it up but still enabling us to scan from 50, we should be able to go to about 2,000. So that's much, it's about a 4-time increase in the mass range capability. So instead of being able to do just inorganics, then maybe we can start to do organics, biological samples with that extended mass range. But the real objective here is to take advantage of the lower voltages, lower operating voltages, and the smaller scale, lower power, lower mass, weight, and integrate this into a smaller handheld unit. Instead of having 2 people to carry around this instrument, then we can have just, something that you carry in your hand and you use to do field analysis. So instead of having a GCMS that's mounted in your truck or your vehicle out in the field, this is something that you could take on person and do, quick analysis on the battlefield or the forensic site or something like that.
Okay, Patrick, we have a question from Nicholas Scott. Given the materials that you are interested in measuring, what are your expected uncertainties in producing this instrument? And how does scaling things down influence bias versus variance?
All right, so that's a great question. So part of this investigation, of course, is proving the performance in an existing instrument, right? So there are trade-offs anytime you scale something, but the benefits in the reduced size and the reduced operating voltages are pretty significant and enabling us to make something much smaller. Uncertainty, variance, a lot of these things in the mass spec field are handled with software and duty cycle of the instrument. So, you're running, you're getting a mass spectrum every 50 milliseconds or something like that. The instrument software is recording those, doing statistics. So there's quite a bit of capability to, have a robust software system to increase the reliability of the signal. All right, so there's some good questions. So this is the miniature ceramic ion trap mass spectrometer chip project. And what we've done here is we've made a small centimeter square ion trap chip using metallized ceramics. So metallized ceramics are a traditional electronic packaging technology. And what we're doing is we're miniaturizing mass spec components using the material and fabrication capabilities of electronic packaging and semiconductor microfabrication. So using these two methods, we're able to get much smaller lower power, lower mass, mass spec components. This poster is about the ceramic ion trap chip. We're also investigating a micro gas chromatograph on the chip as well. And we'll be using that as the front end separation method for the material identification on the back end for the ion trap chip. So to prove out the ion trap chip performance, what we've done here is we've integrated the chip into an existing GCMS, a portable unit by FLIR Griffin G460. So in this first image you see here, the small chip and then the conventional instrument ion trap. And what we've done is we used that ion trap, the OEM ion trap, as the integration fixture going into the GCMS. So the first spectrum you see at the top is just the baseline mass spectrum of FC43 or PFTBA, which is a calibrant for mass spectrometry. Okay, and the mass range goes from 50 Daltons up to 450 Daltons. Okay, so that's what you see in the first spectrum with the FLIR G460 ion trap. Now, what we did was we, keeping the experiment the same and integrating our chip into that ion trap, what we've done just as a fixture, we've scanned the mass range. We've scanned the voltage and achieved a mass range of about 220 Daltons up to about 1250. Okay, so there's quite a bit of difference in that mass range, and you can see I highlighted the purple regions or the pink regions there to cover the areas that are the same. So we're missing the first half of the mass range from about 50 to 220 Daltons, but then we pick it up from 220 and we finish off at 450, but then we continue to go out to about 1250. And the reason for this is that, the physics of the way the ion trap works, with the smaller scale, with smaller voltages, you can scan the same masses, okay? But we didn't change our voltages here. We just stayed from 200 up to 2000 volts, okay? And that shifted the mass range, or the operating mass ejection range that we're gonna get for the smaller chip, okay? So in order to recover or obtain those lighter masses, right, from 50 to 220, what we're gonna have to do is modify the RF voltage supply. And there are two ways we can do that. We can either change the analog electronics, or we can go ahead and we can truncate that voltage signal through RF attenuation. This project is the Miniature Ceramic Ion Trap Mass Spectrometer Chip Project. And the main idea behind this project is to create new miniaturized mass spec components to enable handheld mass spectrometer instrumentation, specifically a GCMS handheld unit. So what we've done is we've taken a conventional portable GCMS unit that weighs about 100 pounds and takes 2 people to carry, and we've integrated a metallized ceramic centimeter squared ion trap chip into the ion trap assembly. So using the ion trap assembly as an integration fixture, we were able to run the ceramic ion trap chip in the GCMS. So looking at the first spectrum here, that is a spectrum of PFTBA from 50 Daltons to 450 Daltons. The full scale spectrum. Now, what we did was we plugged in the ion trap chip into the same assembly, running the same experiment with the same calibrant, and we obtained a mass spectrum from 220 Daltons all the way up to about 1250 Daltons. Okay, and the reason for that is at lower voltages, the ion trap chip, due to its smaller scale, will eject higher masses. Okay, so the two pink regions are redundant. Okay, and this is the miniature ceramic ion trap mass spectrometer chip project, and basically what we've done is we've fabricated a miniaturized centimeter square ion trap chip, and we've integrated this into a Griffin G460 GCMS unit. And testing the unit before the integration, we were able to get a 50 to 450 Dalton mass range for PFTBA. But then going ahead and doing the same experiment, but with the chip integrated, we were able to get a mass spectrum of about 220 Daltons all the way up to 1250. So we got an extended mass range, but we're missing off on the early 50 to 220 Dalton part of the spectrum. And the reason for that is that the chip ejects masses at lower voltages. Okay, so in order to recover the initial mass range of 50 to 220, we've got to modify the RF power supply. And there's two ways we can do that. We can either change the analog electronics, or we can use attenuation techniques, devices to scale the voltage to cover that initial 50 all the way to 450, which is standard inorganics. But then as we extend out in higher voltages, which the chip can withstand, we'll be able to have an extended mass range. So we're predicting we can go probably from 50 up to 200, up to 2,000 Daltons. So we have a extended range, mass scanning capable ion trap chip that is a centimeter square, low power, low mass, that we hope to integrate with GC on a chip for initial separations with material identification with the ion trap chip, and taking these components and integrating them into a handheld unit.
Okay, we have a question from Stephanie. She says, first of all, thank you. And as I'm the only one, and she's the only question, in which specific field of analysis will be usable on the field, and how practical?
So this technology is currently under development for a handheld unit. And the goal for us is to take these miniaturized mass spec components, integrate them into a handheld unit for the use, the use in any field. We're looking at the mass range as the foundation, obviously, to maximize that, and then looking at sample inlet methods, liquid injection, gas sampling, and then also maybe pyrolysis methods for solids, where you could do these different types of sampling and get the results in the field out of a handheld unit. Now, like I said, it's under development, but I think that a lot of these problems will be worked out in the engineering into practical methods, and hopefully using modular type sample inlet components.
Okay, thank you, Patrick. And I just want to remind everybody that we will be emailing you shortly with your typed out questions throughout the presentation. So you'll have those in hand, and we want to thank everybody for participating today.
Thank you very much.